Hello. I wanted to go over the laboratory this week on Coulomb's law. The first thing I'm going to do is just give a brief overview of Coulomb's law, and then I'll go over how to set up the lab. I'm going to open up a whiteboard first. Okay. Okay. And I'm going to write down the mathematical expression for Coulomb's law. It's F, and I'm going to put a subscript E. So this is a force, and in particular force is the electric force. So we're talking, Coulomb's law is describing the electric force between two charged particles of very small mass. So the electric force is equal to K, which is a constant, we'll talk about it in a second, multiplied by Q1, which is charge 1. That's referring to the charge on charge 1. And Q2 is referring to the charge on the second one. And then it's divided by R squared. K is an electric constant. It's called the Coulomb constant. Q1 and Q2 are the charges on each of the charged particles. And the charges are measured in coulombs. We describe the amount of charge an object has in terms of coulombs. Most things are electrically neutral, so they don't have a charge. But if something has an excess of electrons, it would have a negative amount of charge. If something has a lack of electrons, it would have an overall positive charge. And the charge on an electron is 1.6 times 10 to the negative 19th coulombs, and that would be a negative charge. A proton would have the same amount of charge except positive. So usually you don't see objects with like massive amount of charge on it because one electron only has 1.6 times 10 to the negative 19th coulombs. It's a really small amount of charge. So that's how we describe charge, and it can be positive or negative depending upon whether it's an electron or a proton. And R is the distance between the two charges from like center to center, basically. I mean, we're talking about particles, so they don't really have a space, but R is the distance in meters. Force is always measured in newtons. And K is a Coulomb constant. It tells us how all of these are related to each other. And its value is 9 times 10 to the 9th. Its units are Newton meters squared per Coulomb squared. It's a pretty big constant. It's 9 times 10 to the 9th, right? It's a fairly large constant. So this is kind of telling me that the electric force between charges is relatively large. It makes sense that the force would depend upon the amount of charge that's on each thing, right? So if I have a lot of charge, there's going to be a lot of force, right? If I only have a little bit of charge, it's only going to be a little bit of force. And it also, so more charge, more force, right? These are directly proportional. And on the bottom is R, the distance squared. So the force is inversely proportional to the distance squared. it drops off as 1 over r squared. So as the charges get farther apart and r gets bigger, the force drops off and gets smaller and smaller and smaller. So this is what Coulomb's law is. And the and so that's the magnitude of the force, right? And so when I'm dealing with magnitude, I just want the number, I don't care about the direction. I'm just going to take the absolute value of these charges. So if they were negative charges, I would just call them positive charge if I just want the magnitude of the force. If I want the direction, right, I have to look at the sign of the charges, right? So if I had like a positive charge here and a positive charge here, these are like charges and they're going to repel each other. So this one would experience a force this way, this would experience a force this way. The size of the force is the same on each one. It's an equal and opposite force. It's just pointing in opposite directions along the line that connects their centers, right? The same thing would happen with two negative charges. They would be repelled from each other, and the direction of the forces would be opposite along the line that connects them. And if it was like opposite charges, there would be an attractive force. Again, this force would be the same size, the same magnitude. It's equal and opposite action-reaction force pair. But now it's an attractive force, so the force would be pointing this way on each one. So that's the idea behind Coulomb's law. It can be only used for 2-point charges. Okay, so it's kind of limited in a way, but we can extend it out to, we can think about extending it out to charge distributions, but right now in this lab, we're just going to focus on 2-point charges. And you might notice it looks a very similar to another force that you've learned about in Physics 141, which is the gravitational force between two masses, where you have capital G, universal gravitation constant, mass 1, mass 2 over r squared. Does that look familiar from Physics 141? Hopefully it does, right? It's almost the same. It's like looking like the same exact format, right? So these forces are somewhat similar in a way, right? They have the same thing where the force depends upon the mass of the two objects that are interacting with each other, and it drops off as the distance between them gets bigger. But the difference between these two forces says that that universal gravitation force, if you remember back from Physics 1, 6.67 times 10 to the negative 11, and the units for that are Newton meters squared per kilogram squared. That's the universal gravitation constant. That basically tells us how all of these things are related to each other. Notice that this is a really small number, 6.67 times 10 to the negative 11th, really small, right? So the gravitational force is actually a pretty weak force compared to the electric force, which is rather strong. So those are kind of the similarities and differences, but overall the format of them looks really similar, right? But in the lab today, you're going to do a couple of different things. You're going to look at how charge affects the force, right? So you should see that increasing one of these charges should increase the force. You're going to plot that data on a graph, keeping the distance between them constant. And you're going to be able to determine the Coulomb constant K here from your data. In the second part of the lab, you're going to look at how does changing the distance between the charges affect the force. So you're going to keep Q1 and Q2 the same, and you're going to vary the distance between the charges, and you're going to collect data on that, and you're going to plot it, and you're going to, again, determine the value of K. And hopefully you will get close to 9 times 10 to the 9th. So that's the goal. So I'm going to close this whiteboard, and I am going to share my screen and bring up the lab. So Here's the lab that you will be working on. In part 1, it says go to the link and fix the charges Q1 and Q2 and write their values. Oh, I'm sorry. Part 1 is changing the distance. I switched them around. But part 1, you keep Q1 and Q2 fixed, right? Whatever you choose, that stays the same. And you change the distance between the two charges and record the value of the force between them. Okay? So let's do that. So here's the table that you need to fill out. So let's go to the simulation. Okay, so you're going to go into the simulation and you're going to just click on macro. So let's keep, you can change the amount of force. You can make it positive or negative. It doesn't really matter. Let's make them pretty big. Okay. So Q1, charge 1, has a charge of -7. This funny looking M is the micro. So -7 microcoulombs. That would be times 10 to the -6th coulombs. And charge 2 has 10 microcoulombs, or 10 times 10 to the -6th coulombs. So let's write that in the table, -7 and 10. Okay. -7 microcoulombs. Actually, I'm just going to write it in terms of regular coulombs. So I'm going to write it times 10 to the -6th coulombs. And the other one was a +10 coulomb times 10 to the -6th coulombs. Okay. And so we're going to start them off at 10 centimeters apart and gradually lower the distance between them down to 3. I'll just do a couple of values to help you fill in the table. So, and you can pick whatever charges you want. As long as you stick the same way throughout the whole thing, then you're fine. So let's go back to the simulation. Sorry, I'm going to be jumping back and forth a lot. Let's separate them 10 centimeters apart. The force on Q1 is 62.9 newtons. The force on charge 2 is also 62.9 newtons. And the force is, it's hard to see it, but there's an arrow here. So it's an attractive force because these are oppositely charged particles. So at a distance of 10 centimeters, the force was 62.913 newtons. Let's put that in the table. Sorry, back to the table. So you will type in 62.913. You're also asked to determine r squared and 1 over r squared, because remember, Coulomb's law, there's an r squared on the bottom. So let's calculate that in meters. So it was 10 centimeters, so that's going to be 0.1 meters. And then I square it, so that's 0.01 meters. And then I'm going to take the inverse of that and write that down in the next table. So 1 divided by 0.01, 100. Okay. I'll just do 9 and 8. Okay, and then you can do the rest. So let's check 9 centimeters. The distance between them decreased. Notice that the force increased. So this is an inverse relationship. The force is now 77.670. So let's put that in the table. 77.670. The distance was 9 centimeters, and I'm going to convert that into meters. So I divide by 100. So that's 0.09 meters, and then I square that. 0.0081. And then in this, I take the inverse because the force is inversely related to r squared. So that's why we're taking the inverse here. 123.5. I'm not gonna stress out about significant figures. I want you to focus on the concepts here. I mean, it doesn't really matter because we're not using real life measurement tools anyways, right? This is a simulation, so it's not as big of a deal. All right, let's try one more. Let's go 8 centimeters. Okay, move this over. Okay, now the force is 98.301. 98.301. R squared will be 0.0064 meters squared, and then I take the inverse of that, 1 over that, 156.25. Okay. So notice as I increased the distance, as I decreased the distance between them, the force was going up, which is what we would expect. Right? I will let you fill in the rest of the table based upon your own data that you have. So that's first data collection. Part 2 is we are fixing charge 1 at 5 microcoulombs, and we are also fixing the distance at 6 centimeters. And the only thing that we're going to change here is Q2. So as we decrease the amount of charge on Q2, what should happen to the force? If Q2 goes down, the force goes down as well. So let's do that. Let's set it 5 microcoulombs, 6 centimeters apart, and we'll start with Q2 being 10. Okay. 5. 5 microcoulombs, 6 centimeters apart. And we're going to start Q2 off at 10 microcoulombs. The force on each of them is 124.827 newtons. So let's record that in the table. 124.827. I'll just do a couple more. Let's change Q2 down to 9 microcoulombs. Sorry, I keep jumping back and forth. So we're on 9 microcoulombs, keeping everything else fixed. The force is now decreased, 112.344. Let's do one more so we have at least 3 data points. Now let's make the second charge 8 microcoulombs. All right. 99.862 newtons. Okay, and let's record that in the table. Okay. I will let you fill out the rest of the table when you work through the lab. Okay, so we have collected the data. The last part is to analyze it. Part of going and doing a physics laboratory is not just learning physics, although that is an important part. There's also skills involved. And one of the skills I like to promote is analyzing data, presenting data in a way that makes sense, and communicating what the data actually means. Being able to look at a graph and say, what am I learning from this graph? Okay. I think many employers would appreciate a skill like that. Make me a graph. Okay, here's a bunch of data, right? Do something with it. Make me a graph and explain it to me, right? Explain it in a way that makes sense. So let's do that for our data here. We're going to use Excel. The first thing I want you to do is know that you can find Excel through CCAC if you don't have it already. So let me share my screen and I can show you where to find it. So if you go into like your email, CCAC email, and you click here up in this left-hand corner, these are all of the apps. PowerPoint, Word, OneDrive, whatever. Excel is here, so you can click here. And create a new workbook. And Excel is used to input data and create a graph of it and analyze that graph. So let us put in the data for the first set of data that we had. So what I'm going to do first is, sorry. The first set of data that I'm going to input into Excel is from part 1. And that will be the data from this table right here. And you want to make a graph of the electric force on the y-axis and R on the x-axis. And then you want to make one more graph of the electric force on the y-axis and 1 over r squared on the x-axis. So I'm going to, in Excel, I am going to start inputting my data. So at the top, I'm going to say FE, electric force. And then in the next column, I'm going to write R, and then in the next column, I'm going to write 1 over R squared. And each of these is going to be a set of data. So the first one, the force was 16.913. So I'm going to type that in here. The distance between them was 10 centimeters. Let's put everything in meters so we're all the same. 1.01 meters. And 1 over r squared from our table was 100. I will do the next couple real quick. Sorry. 156.25. Okay. All right. All right. So here's our data, and you would have more data here because you are going to collect more data in the lab, right? But I just did 3 sets. So now I want Excel to make some graphs for me. I want to be able to visualize this. So what I'm going to do is I'm going to click Insert, and I'm going to click right here, Scatter Plot. Now it hasn't plotted anything yet because I haven't told it what data to use. So I'm going to click on the table and I'm going to right click on series and I'm going to click format. And there's X values and there's Y values right here. So you want to click on like chart and then data. You can also click select data here as well. And in the X values, click you're going to click source. So that's the data. And in the X values, you're going to click here. Sorry. Okay, sorry about that. It's a little different when I'm using it in the browser, but it's all right. Okay, so I rearranged things a little bit because you want your X values to go first in the column and your Y values to go second in the column. Okay, and so let me start over again. These are our X values, which is the distance between the charges, and these are our Y values. So I'm going to select this data and I'm going to insert that here. And I click insert scatter plot. Okay. And notice the force is on the y-axis, right? Because the value should be between 0 and 100, right? So that makes sense. And the distance between them is from 0 to like 0.12. So that's looking correct. Okay. You might have to say that the data fields are split up by columns if it doesn't do that automatically for you. So in here you can write electric force versus distance as your chart title. You should always tell me what you're charting, right? If you want to put axis information, you can mess around with that here. But as long as in the chart you have something that tells me that this is electric force versus distance, I'm fine with that. Let's do the electric force versus 1 over r squared, because that's another thing you have to plot in Excel. So what I'm going to do is, again, I'm making two columns. The first column is the stuff that I want on the x-axis, and the second column is the stuff that I want on the y-axis. I'm going to highlight my data, and I'm going to click Insert, and I'm going to click Chart, Scatter Plot. Notice here, it looks more like a straight line. So what we want to do is determine the line that fits through this the best. Okay, and then we're going to analyze what does that mean. So give me a sec. So let's see if I can make a line of best fit through this data. This is electric force versus 1 over r squared. To get a line of best fit through these, you're going to click on the data. And you want to put a trend line through this data. So you're going to toggle the trend line to be on. And we want a linear trend line. And let's make it pass through the 0. So we're going to set x-intercept to 0. Y-intercept to 0, sorry. The other thing that we want to do is put the equation of the line on the graph. So the equation of this line is y equals 0.6291x. All right, so what does that mean? Okay. So we all remember y equals mx plus b, right? In this case, b is equal to 0, the y-intercept is 0, so I'm just going to take it off. On the y-axis, we have the electric force. So electric force is like our y, right? Fe. And x is 1 over r squared. Right? So the question is, what is the slope of this line? It's 0.6291. From Coulomb's law, electric force is equal to K Q1 Q2 over R squared. So the slope here is what's left over in Coulomb's law. It must be equal to K Q1 Q2. So let me write this on a whiteboard so it makes more sense. One over R squared. This is Coulomb's law, right? And we graphed that. Y, this corresponds to y, and 1 over r squared corresponded to x. So this left over must correspond to the slope. And the slope from our graph was 0.6291. You might have something different if you chose different values for Q1 and Q2. That slope has to be equal to K Q1 Q2. And in our data, Q1 was -7 times 10 to the -6 coulombs, and Q2 was 10 times 10 to the -6 coulombs. Everything is just using the absolute value for the charge here because we're not worried about the direction of the force. So I'm going to set that equal to K 7 times 10 to the -6 coulombs and 10 times 10 to the -6 coulombs. And from this, we can use the data that we collected from the experiment to solve for the Coulomb constant K. So I'm going to take my slope 0.6291 divided by the two charges here. And I get a value for K, which is like 8.99 times 10 to the 9, which is close to what the value should be, 9 times 10 to the 9th. So we're pretty much right on. So that's the idea. You're going to take data, you're going to plot it, and you're going to analyze, what does the slope of this data mean? What am I getting out of this, right? And you're going to do that for a lot of labs this semester. So that's the idea. And you will do the same thing for the second part, where you keep one of the charges constant and the distance between them constant, and then you vary the second charge. So you'll be plotting electric force on the y-axis, and you'll be plotting the charge on the x-axis. And from that, you should be able to determine the slope and use this to help you figure out the slope and determine K again. So sorry for some of the technical difficulties. I hope that makes sense to you. But if you do have questions and you need to walk through it again with me, set up a meeting on Zoom, and I'll see you soon. Okay, bye.